Hi, welcome back to Calculus. Today we are looking at section 5.4, the fundamental theorem of calculus. As you might expect from an audacious title like that for a section, this section is really kind of sort of important. In here, what we're going to see is we're going to be able to tie together derivatives and these integrals, and that's really pretty cool. So hang on, buckle up. We're going to have some fun here. Before we actually get to the fundamental theorem of calculus, though, we have to first lay out the mean value theorem for definite integrals. If memory serves, and it's been a while, so it's possible I'm wrong, but if memory serves, this is an integral part of trying to prove the fundamental theorem of calculus, which comes next. But we're going to lay it out here anyway, because it's fun. It says, if f is continuous on the interval ab, then at some point x equals c in that interval from a to b, f of c is equal to 1 over b minus a times the definite integral from a to b of f of x dx. Remember this right-hand side, if you watch section 3, that's just the average value of the function on ab. So what the mean value theorem for definite integrals is saying is that somewhere in between a and b, you have to cross that average value for the function. So that's what the mean value theorem says. And now we're going to move on and we're going to look at the fundamental theorem of calculus part 1, because there are two parts. So hang on, let me get it on the board and we'll look at that. Alright, so here we go. The fundamental theorem of calculus part 1. It says, if f is continuous on a closed interval ab, then the function capital F of x, which is equal to the integral from a to x, oh boy, that's fun right there, we'll come back to that, of f of t dt is continuous on the closed interval ab and differentiable on the open interval ab, and its derivative is f prime of x is equal to d of x, the derivative with respect to x of that integral from a to x of f of t dt equal to f of x. Oh boy, so here's what's happening. We're defining a function now from a point to an x value that is potentially mobile. Moving around, right? We have a function of this x value, so we're going to be moving that around. And we're defining it to be the derivative of the area underneath this curve, essentially. Okay, kind of, sort of, essentially, that's how we're defining this. So that's really kind of fun. We have a derivative, we have a change in the area under the curve as we move this x value along the x-axis. Or as we look at, as x moves along the x-axis, maybe. And so that's really pretty fun. And I really hope that what you're seeing here is a connection to some notation that we saw before. We have this capital F of x, and before we used that as an antiderivative. And so that's going to be a really important concept here in just a few minutes as we get farther into this section. But we can see it kind of set up here. We have that the derivative of this f function is the derivative of this integral is that little f of x. And so really what we're looking at here is that here's that little f of x and it is the derivative of that capital F of x. That's really what it meant to be an antiderivative. So we're going to come back to that here in a minute. One other little note that we will need here, and we'll look at it more here in just a minute when I do some examples. We can put other things than x up here. Okay? We can have what almost looks like a function of x up there, and we're going to have to basically utilize a chain rule if we have something else up there, and we'll see that in one of the examples. And the other important point here is that this always starts at a number. If these two things are switched, we're going to have to take advantage of our rules for definite integrals and switch that and use an opposite sign. So anyway, let's get into those examples and we'll see a little bit more about what I'm talking about. Alright, so I have on the board here two different examples using the fundamental theorem of calculus part 1. First, we want to find dy dx when y is equal to the integral from a to x of t to the fourth minus 5 dt. So a couple of things here. This one is set up just like we want. As we'll see in a minute, this other one that's hiding behind me, it's set up messier and we're going to have to deal with that. But let's look at this one first. So what we have here is, here's my inside function, the function that's inside the integration, t to the fourth minus 5. This is exactly the setup that we want to be able to utilize part 1 of the fundamental theorem. So what we know is that this derivative of y here is equal to the derivative of this mess, and now it really looks exactly like that theorem, and all we have to do is plug in x for t, and that works really, really well. Okay, so that was just beautiful, and so we get the, we've used it. We've found that derivative. For the second one, I have y is equal to, this one's a little messy, so hopefully you can read it. The integral from 1 plus 3x squared to 4 of 1 over 2 plus e to the t dt. Oops, I forgot a d dx. So when we do this and take its derivative, I used y prime this time. The first thing I noticed was that the order of integration was backwards. The number is supposed to be at the bottom, and x is supposed to be up at the top. So I switched it, but remember, if you switch the order of integration, you need a negative sign. So I got a negative sign. I just dragged it out in front of that whole thing. So we have the opposite now of the derivative from 4 to 1 plus 3x squared, still of 1 over 2 plus e to the t dt. This is where things get just a little bit weird. We don't just have x up at the top of that integration anymore. So now when we take the derivative of this, we still plug in for t, but we're plugging in that 1 plus 3x squared because it's not just x anymore. It's that ugly mess up there. So we get the opposite of 1 over 2 plus e to the 1 plus 3x squared, but we need more. Because it's not just x up there, we're really using a chain rule when we take this derivative. We need to take the derivative of that 1 plus 3x squared and multiply it. Okay, this is a chain rule that we're doing here, and so make sure that if you have anything other than just x up there, make sure you take that derivative. When you do, the derivative of those parentheses is just going to be 6x, right? 2 times 3 will give me 6. And so I combine the 6x with the negative sign that was in front and just plop that on top. We get negative 6x over 2 plus e to the 1 plus 3x squared. So that's a big, ugly mess, but there we go. All right, next board, we're moving on to part 2. I like this part better. I think this part's really, really cool. So hang on and we'll look at it. All right, so here we go, the fundamental theorem of calculus, part 2. It says, if f is continuous on the closed interval ab and capital F is any antiderivative, doesn't even matter which one, and that's going to be kind of nice here in just a minute, of little f on the interval ab, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. In other words, find that antiderivative for the function on the inside. Once you do that, plug in a and b and subtract. And you have that, what you get is you get the area under that curve. Well, I mean, technically, it could be negative, so it's not always really an area, because area is positive, but you get the stuff in the space that's underneath the curve, I guess. And that's really pretty cool. So we have this wonderful connection between antiderivatives and derivatives, integration and derivatives, and it's all tied together here in the fundamental theorem of calculus. And so this is pretty fun. I have 3 examples that I'm going to do for you. So it might take me 3 boards, but we'll see. Might just take 2, but anyway, we'll see. So buckle up and let's do some integration. All right, so here's my first example. The definite integral from 0 to 6 of 3x squared minus 5x plus 1 dx. So first I found the antiderivative. This one's nice. It's just polynomial. So remember, powers go up by 1 and then divide the coefficient by that new power. So 2 becomes a 3. 3 divided by 3 gives me a 1 there. This becomes x squared because it goes up by 1. 5 divided by 2 is 5 halves. And then the 1 turns into an x. There are no x's. We put it back in. And we get x, and then we don't forget our c. Except as we're going to see, we don't need it. And we'll see why in just a second. So then I plug in 6 and 0. And if I do that, you can work it out for yourselves. But for f of 6, we get 132 plus c. And for f of 0, we get c. But what happens then is when I subtract those two, because remember, that's the last part of finding this definite integral, is once you have that antiderivative, subtracting those two values. 132 plus c minus c is just 132. And it turns out that that c will always drop out. And it actually goes back to part 2 here of the fundamental theorem of calculus that just said any antiderivative. So we can always use the antiderivative where c is just 0. And that won't be a problem. All right, I have 2 more examples. Let's get the next one on the board. All right, here's my next example. Find the definite integral from pi over 2 to 3 pi over 2 of sine x dx. Now, be really careful with this antiderivative. We know that cosine turns into a negative sign. So since I have a positive sign, my antiderivative here needs to be a negative cosine x. It's really easy to forget that negative sign. Okay, so just be very careful. Remember, cosine's derivative is a negative sign, so we need to put that negative back in here. So I get that this definite integral is equal to negative cosine x, and this notation here just means evaluated at pi over 2 and 3 pi over 2. So I plug in 3 pi over 2 and pi over 2, so I get the opposite of cosine of 3 pi over 2 minus, again, be careful with those signs, although in this case it wouldn't end up mattering, but minus, I still have that negative cosine of pi over 2, but if you know your trig functions, the cosine for 3 pi over 2 and for pi over 2 are both 0, so we just get 0 plus 0, which is 0, and there we go. All right, the last one's a doozy, so buckle up. This is going to be really fun. Pay attention. All right, so here's my last example, and it's pretty wicked. Let's take a look at it. The integral from 0 to pi over 3 of cosine x plus secant x, whole thing squared, dx. All right, so we have some serious problems here with this particular one, and so we're going to have to be very careful. We don't have a way to integrate with the square as of yet. We have a binomial square where we have trig functions on the inside. We can't do that yet. So instead, we have to actually expand the square. So if you multiply cosine x plus secant x times itself, you get cosine squared x plus 2 cosine x secant x plus secant squared x. Now, a couple of really nice things happen here. The first is that cosine and secant are reciprocals. So they just drop out. They turn into 1 when you multiply them together. And that's where I get this 2 down here on the next line. The second really nice thing is that we know the antiderivative for secant squared. It's over here, tangent x, and we'll get to that in just a minute. But we still have this cosine squared x. That's really a chain rule, and we can't do that one yet. So I had to go into the back cover of the book and find a trig identity to change this so that we didn't have the square anymore. I found one that can turn cosine x into cosine 2x plus 1 all over 2. And then I rewrote this as 1/2 cosine 2x. And then I took the half from the 1 and 2 and added it to the 2 to get 5/2. And this works because now I can find the antiderivatives of all 3 of these pieces. So the first one is the hardest one, but the antiderivative of cosine is sine. With the 2 on the inside, remember that we have to divide by 2, right? Because this would be, if we think about sine 2x, if we took its derivative, we'd have to use a chain rule and multiply what we got by 2. So going backwards to find the antiderivative, we have to divide by 2. Well, we already had a half. If we divide it by 2, we get a quarter, right? Same as 1/2 times a half. So we get 1/4 sine 2x. The 5/2 is wonderful. It turns into 5/2 x. And as we said a minute ago, the antiderivative for secant squared is tangent. So this is where knowing all those derivatives can come in very handy. And we're going to evaluate this from 0 to pi over 3. We do that, we plug in all that mess. You'll see here's where I plugged in pi over 3, and then here's where I plugged in 0. The nice thing is here, you get the sine of 0, which is 0, so that piece drops out. 5/2 times 0 is 0, because I didn't need that parenthesis. So that drops out, and the tangent of 0 is 0. So all the subtraction goes away, we don't even need it. So the sine of 2 pi over 3 is square root of 3 over 2. I get 5 pi over 6 from that middle piece, and I have the tangent of pi over 3, which is the square root of 3. So it's worth noting here, when I do this multiplication, I'm going to get 4 times 2 is 8 on the bottom, so I have the square root of 3 over 8 from this first piece. So I just rewrote that square root of 3 with a denominator of 8, called it 8 square root of 3 over 8, and then I combined those 2 pieces to get 9 square root of 3 over 8, and you can't combine 5 pi over 6 with anything. It's its own weird, messy little bit. So there we go. That is our definite integral for that problem. It's a mess. Go back and watch that again, because you might need to watch it 2 or 3 times to actually figure out what just happened there. So have a good day.